My name is Jim Kerevala from Shackleton Energy Company, and I want to approach the issue and the challenge of what we're doing here from a different direction from the very wonderful presentation we just saw. What we're doing at Shackleton Energy Company is a very large-scale program dedicated to, in fact, saving the planet. And the pathway that I will show you will enable all of us, everyone in this room and around, to become part of that process. And every project that you're doing, whether it's something like Manu's, whether it's a project that you're thinking of, anything that you're doing, even as a single stage project, will have an effect on this program. What we are doing is establishing propellant depots in space, gas stations in orbit, if you like. When you have gas stations in orbit or propellant depots, you can build spacecraft and vehicles that are reusable. When you build reusable spacecraft, you change the entire launch cost dynamic of your ground to low Earth orbit launch economics. That is one of the big impediments to getting into space on a large scale. The key advantage and the key opportunity is if you can get those propellants from a lower gravity well, i.e. somewhere lighter, which is less energy, which then requires less cost. And if you can do that over a long period of time with multiple customers, you basically have a supply chain business. And we know this works because we've done it before in the mining, resources, and oil and energy sectors. This is how business is actually done and how markets are created. So we are working on a very large-scale oil exploration type program that we have now put together over the last 5 years, and are working with capital infrastructure and investment banks to start getting this capitalized with the bond financing to commence. It is a human-tended industrial astronaut corps with many tens of vehicles and units in space, and it's a paradigm change of how we undertake space development. Let me give you some context here and how every one of us is involved in this. Over the last 50,000 years, as a civilization and a species, we have always developed and undertaken any of our activities with frontiers in place. We have had open geographical, resource, economic, and visionary frontiers. And those frontiers are basically almost came to a close about 100 years ago as we reached the west of the Americas. And this current economic civilization, I wouldn't say Western, but this current global economic civilization has now reached more or less the geographical frontiers. It's our job in this generation to reopen that frontier so that we don't see some of the economic consequences that we've been witnessing over the last few years recurring and enhancing. And those last few hundred years, we have also increased our ability to industrialize. And industrialization, if we can do it with environmental balance, gives us the strength of economies of scale and opportunities to reach and serve markets with new capability. So the one key thing, as we go from our citizen-based projects and our individual projects that we can start within 24, 36 hours, to thinking about the future, the key fulcrum point is access to water in space. That's the key thing, the most important thing you should really take away as a long-term concept. If you have water in space, you have power, energy, and life support. And that's a starting point for a great many deal of things. And there are three major issues that then underpins, and I'll explain why. Now, the first issue is that by mid-century, we are going to have a population of between 9 to 11 billion people on the planet, according to current estimates. That population is also going to have a high resource requirement. As quality of life standards and communication and distribution of materials increase, those resources are going to become even more scarce or more economically difficult to extract. Even more critical than the resource issue, because there are always new processes to extract and separate minerals from ore, is the energy issue. This is an absolutely critical problem that we are going to face by mid-century. We are facing a terrestrial energy gap. With those 10 billion people by mid-century, our power consumption as a planet may go from our current 15 to 16 terawatt electric, may even double by mid-century to 30 terawatts electric or more. Now the challenge about that doubling of energy is that if we stack together all of our terrestrial energy provision capabilities from petrochemical, nuclear, geothermal, renewables, even stick fusion on there if you want to put a potential concept, we still have, by mid-century and beyond, this energy gap increasing. If we have that energy gap, we have an increase in conflicts, regional instabilities, and a lack of distribution of resource. Closely tied with energy, of course, is the ability to provide fresh water to populations of the Earth. So these are major challenges, and actually they are the big elephants in the room, that all our regional and local energy efforts that we make today with solar panels, wind energy, we really, what we're doing is charging for a cliff. We're charging towards a cliff at a massive pace and trying to blow in front of us to slow us down a little bit. This is the challenge that we're facing, and we have to do something on a really major planetary scale to solve these critical energy problems. Now this may not happen with luck by mid-century, but if we just carry on the way we're going, it's going to happen at some point. And we, as this generation, are almost the first generation that are individually empowered to do something about this. And I'll explain how doing all this together we can. Now there is one major technical solution that can solve this problem. And that major technical solution, and chaps like Ed, sitting there in the back, standing in the back with the white hair, know this very deeply, and others here, is space-based solar power. Now, space-based solar power, it offers the best technical opportunities for providing massive amounts of power generated from capturing sunlight from the sun and then beaming that back to terrestrial receiving stations on Earth. The only problem is it's the worst economic proposition in history. There is no business model that allows us to launch these space-based solar power stations from Earth at the current cost per kilowatt hour of electricity, and then make a profit with an internal rate of return that will satisfy even the most benign investor. So what do we do, and why is all of this? Well, just a quick 101. The reason why it's so difficult and expensive to get off Earth is Earth sits in a very deep gravity well, surrounded by a very thick atmosphere. These are the two impeding challenges that the entire space industry has faced. Why the rockets are built the way they are today, in the shape they are, with the concept of operations of expendable hardware and separated by stages. But if you could build those space-based solar power stations from resources off the Earth, from a location in a lower gravity well, then you start getting some economic sense. Now, if you can then resupply those vehicles and those systems with propellant depots, gas stations, using water sourced from the moon, turning that water by liquefaction into liquid hydrogen and liquid oxygen, that propellant then underpinning a manufacturing and integration set of operations in space, now you are talking about a closed loop architecture where you can really start to create large space infrastructure to undertake these programs. Well, this all sounds great, but this sounds like science fiction. How do you do this and enable the business model and the investment case to close so that we could start that this year, that we could start this program this year and get going? Well, Shackleton Energy's business model is this: propellant depots, tankers, refineries in space to undertake these activities of refining these propellants. And we have modeled over 70 business streams and a fully integrated economic and technical model and analysis with a team of over 100 people now who have put this together as a program for which we are now raising capital. When you have this infrastructure in space, you can start solving some of the real major planetary issues within 2 decades. Space debris is a classic impending problem. There is an issue called the Kessler syndrome. The Kessler syndrome is a cascading continuance of constant collisions in space. When one satellite collides or fragments, all of those other fragmented parts of our spacecraft create new hazards and increase the risk of further collisions, and then that cascades onwards. So we want to be able to avoid that by having the ability to really use vehicles that can be refueled in space to undertake missions with as much delta V or energy as required. And of course we have major issues of planetary protection and asteroidal utilization. And so when it comes down to us as individual citizens or small teams starting from scratch, what is it that we can do together with our friends, with our colleagues, to really participate in it? So let me show you a little bit about the background of where this team came from, and you can maybe have some context and some resonance of where the teams that you can create, like Manu's and others, that you can actually solve real problems that will form business streams for you within 36 to 60 months. So the idea being, you start your projects now, and you iterate, you make mistakes, you learn, you keep pushing forward, and you undertake 10 cycles of flights over, say, 36 months flight programs. By that time, you'll have a business that will fall into a slipstream of new industries forming. That's how it works, and that's how you are really at the very earliest sweet spot of opportunity here. So our teams have had some of the greatest expeditionary experience in the world. We've led teams more than 8 kilometers into the Earth's crust in some of the deepest cave diving teams, and in fact, there is a 70-man team, a 70-person team undertaking a record-breaking attempt with Discovery Channel and National Science Foundation right now as we speak, over a 3-month mission. And for those missions, we've developed our own life support infrastructure and architecture. We've built our own rebreather systems that even US Special Forces and other groups use now, and these may become mainstream for the entire global scuba diving industry by the end of this decade. So that's a great deal of life support system experience. We've built our own autonomous robotic systems, both for underwater navigation, led expeditions across Antarctica and extreme environments, and even undertaken fully autonomous 3D mapping missions with vehicles with a high degree of artificial intelligence, maneuverability, propulsion, and onboard computing capability. And we use those systems to baseline for NASA and other groups, for example, the Europa missions. And we formed this baseline architecture of melting the ice lakes of Europa, the ice-covered lakes of Europa, and deploying our DepthX deployable undersea space vehicles for non-terrestrial planets. I myself been part of rocketry groups back in the 90s. I was chairman of a rocketry group, and we built our own liquid oxygen polyethylene rocket engines and vehicles. We launched at several tens of thousands of feet back then. And that was 20 years ago. We were able to build those vehicles and those systems then. Now imagine with the software capability, the communications, the onset of the internet, what you all can do today. It would be extraordinary. The options are there. Another company I was involved with for 10 years was a spacecraft manufacturer called Surrey Satellite Technology. Now Surrey Satellite Technology back in Europe basically started as a small team of 4 people building a satellite out of components that you could buy from Radio Shack. They started that in 1980. And from then on, it's become a company worth hundreds of millions of pounds, and developing a number of spacecraft with over 30, 40 spacecraft being launched by now. Other members of our team have built our own autonomous mining vehicles that are being tested in Chile and Canada right now. And these are teleoperated robotic vehicles where the operators for these mining vehicles actually sit in cabins away from the mining face, and you can actually then operate those vehicles remotely. These technologies are all technologies that we have access to as individuals and teams and small teams. With a computer, an Arduino architecture and other capabilities, we can basically do, one person has the leverage of 100 people 30 years ago. So this is the power of the time that we live in right now. And when you combine all that engineering and what has really started as individuals bringing teams together, doing what they found passion for and then engaging with, and then building that forward into companies and projects, what you then have, before you know it, is a skill set and a capability that allows you to then tackle major problems. And you can take, for example, in our case, our expedition experience, our mining and teleoperation and robotics capability, and you actually now have a platform for an industrial astronaut corps, which is the program that we're undertaking here. And when you then extrapolate forward into some of the designs and architecture for the missions and the programs to be undertaken, what looks like science fiction today is all based in engineering, thinking, prototyping, and architecting for missions and concepts that are based in experience of industries today. So, for example, in some of the prototype mining vehicles on the lunar surface, when you're in 16G, do we employ conventional mining techniques? Will there be new vehicles or approaches we can use? When the phase 2 of our robotic infrastructure is on the lunar surface, we'll understand better the characteristics of the ice and the water within those lunar craters, and then we can decide which mining equipment are actually going to be required. Is it going to be something that extracts water from a solid sheet of ice at 30 Kelvin, or is it going to be permafrosted regolith, which is going to require different extraction methods? So those details we don't yet know. We need our robotic precursor vehicles on the ground first. But all of these techniques are available to be built and prototyped on very small scales very early on. And as you build out and expand those architectures, you will recognize that there will be, let me just back up here, there could be many components that you could look at when you think about an architecture like this. My point being, think about what major businesses are in play right now. What are the directions that the industry is going, and where can you start a project that can add value to small subsystem components, where your team can get an SBIR or a small research grant or a commercial grant or a commercial contract to then undertake a specific project for a specific problem and challenge an issue. You can look at concepts. There are freely available technical papers and architectural papers on many of the issues facing mainstream industry as we move forward now for programs like this. To illustrate in a little more detail our architecture, we have a 4-phase program. We are launching crew and hardware operations into low Earth orbit and first prototype depots within 5 years of program start. And those depots will be serving commercial and federal customers. Once those revenue streams have been generated and proven out, we will then start loading equipment onto the surface of the moon at the chosen camp of operations. And you basically have then a tanker supply chain forming where we will extract that water, bring that water down in transport back to low Earth orbit into our water tankers, via our water tankers to our refineries, and then store that in the depots. Those tankers will then return back to the lunar surface for replenishing as a full industrial supply chain. When you are looking at a business stream like that, of course it's very important to be able to close the economic loop, and that's something we have done and spent many years with our customer partners focusing on. So what could we do if we had access, and if you had access to some early stage flight opportunities for microgravity experimentation? There are a number of things we could do, and as you saw from Ryan's paper previously and others, there is much we can do on human biomedical and other biology issues in space. This is a big field of opportunity. In addition, both in space and in cold traps on non-terrestrial surfaces, there are a multitude of experiments that can be done on ultra-cold operation. What is the behavior of materials, electrics, fluids, lubricants, when you're in either ultra cold or low gravity environments, how they affect. Fluids management is very key. When you're transferring fluids, for example, in a program like this, what about sloshing, cryogenic storage, the issues of boil-off when you're storing cryogenically cooled propellants for a long period of time, you get issues called boil-off because basically these very low temperature fluids can permeate through many materials. So you have a range of topics and subjects actually going into the hundreds. There are hundreds of things and problems a small team of 1, 2, or 4 people could form a project to address and attack. And it's quite possible that those projects have an immediate relevance today to mainstream industry. And it's very, very likely that within a period of 24, 36, 48 months, a skill set developed in solving any of those problems will form into a company that can provide services under contract as a subsystem supplier to other manufacturers. So that's the context and the concept of what we're doing here and what can be done. And I hope you enjoyed that introduction to Shackleton Energy, and happy to answer any questions. Thank you.